Hi there. We know that stars shine because of the energy produced via nuclear fusion reactions taking place in them. But have you ever wondered why nuclear fusion is the only preferred solution to the energy output in stars? In this video, we'll explore the possible energy sources in stars and learn about some of the fundamental reactions taking place in the most common stars that we see in the sky. Let's begin. The lifetime of a star can be measured by the amount of fuel available to it for burning. In other words, the time for which it can sustain its power output. So what are the different options for producing this energy in a star? Let's explore some of the common answers that come to mind. The first one is chemical energy. Chemical energy is the energy generated in chemical reactions involving electron orbitals in atoms and can generate around few electron volts per atom. Therefore, these are far insufficient to account for the stellar energies. That's because electron volt is a very small unit of energy. Since we just mentioned electron volts, let's review the units of energy and take a minute to understand how much is an electron volt. Now you know that 4 joules of energy is required to raise the temperature of 1 gram of water by 1 degree. This is approximately 1 calorie. 1 joule, on the other hand, is defined as the work required to move an electric charge of 1 coulomb through an electric potential difference of 1 volt. Hence the name electron volt. In other words, 1 joule is also the work that you do in lifting an apple, a medium-sized apple, to a height of about 1 meter against the force of gravity of the earth. To give you an idea, here is a small list of energies required in everyday life in units of electron volt. For instance, the thermal energy of a molecule at a room temperature is around 0.04 electron volt, while the electron striking a color television is 20,000 electron volt. Remember also that 1 electron volt is much smaller than a joule. Since chemical energy cannot power stars, let's consider the gravitational potential energy. The energy possessed by an object due to changes in its position in a gravitational field is called the gravitational potential energy. In order to get an estimate, consider a sphere of radius r made up of mass shells of thickness, say, dr. So for each shell, we can then have volume as 4 pi r square dr, density, which is also a function of r, as rho of r, and mass as 4 pi r square rho into dr. So each shell now will have a gravitational potential energy du, which can be given as minus gm of r dm by r. Assuming that the density remains constant, mass, which is a function of radius, so m of r will be equal to 4 by 3 pi r cube rho bar, where rho bar is the average density of the sphere. So the gravitational potential energy of each shell can be given by this expression, minus 16 g pi square rho bar square by 3 r to the power 4 into dr. If we now integrate over all the radii, we will get the gravitational potential energy of the whole sphere. In other words, this is the energy, or this was the work done that was used in bringing all of the particles in the sphere and combining them together. So this potential energy is given by the expression minus 16 g pi square rho bar square by 3 r to the power 5 by 5. But we know that the average density is nothing but the ratio of mass to the volume of the sphere, which in turn gives the gravitational potential energy of the uniform sphere as minus 3 by 5 gm squared by r. So potential energy is only dependent upon the total mass of the sphere and its radius. Notice that as r becomes smaller, the gravitational potential energy becomes more and more negative, implying that energy is being converted to other forms such as heat and light. So in a star such as a sun, which radiates its heat into space, the gravitational contraction might produce the luminosity that we get as sunlight. But then the question is, can the entire energy of the star be radiated away? Or is it only a small fraction of it? How do we determine that? The answer to this question lies in the virial theorem, which states that for any system of particles in equilibrium under the influence of a force, the total time averaged energy is always half of the time averaged potential energy of the system. In other words, kinetic energy is equal to minus half of the potential energy. Notice that kinetic energy is always positive and gravitational potential energy becomes more and more negative as the system contracts. This implies that for a system in equilibrium, only half of the total energy can be radiated away. Kinetic energy will increase if gravitational potential energy becomes more negative, which essentially means that the gas is becoming hotter when it is compressed. So now that we know for a spherical distribution of mass, the gravitational potential energy is given by minus 3 by 5 gm squared by r, which means that the total energy will be half of that value for a system in equilibrium. In other words, the total energy will be minus 3 by 10 gm squared by r. Let's take Sun as an example. So if the Sun was created by a collapsing cloud of gas, it must have released some amount of energy, let's call it delta Eg, during the formation of Sun. This energy must have been released as radiation. So for the current parameters of the Sun, which has a mass of 2 into 10 to the power 30 kilograms and a radius of 700 million meters, this quantity delta Eg, that is the energy that was radiated in the formation of the Sun, comes out to be around 10 to the power 41 joules. But the rate at which Sun can emit this energy, assuming that the rate of energy production and radiation remains constant over its lifetime, can be given by dividing its total gravitational potential energy by the energy emitted by the Sun per unit time. As shown here, the simple calculation shows that if gravitational potential energy were the source of Sun's energy, it would live for 10 million years. However, carbon dating suggests that Moon is more than 1 billion years old, and certainly Moon cannot be older than the Sun. So we can safely conclude that gravitational potential energy is not the source of the Sun's energy either. Notice that the lifetime of an object calculated using the method that we have just used is known as the Kelvin-Helmholtz timescale. Before we move forward, recall the definition of a star we discussed in the video on Introduction to Stars. In case you missed it earlier, a link is provided in the description below and also on your screen. We define an object as a star if it is bound by its own gravity and radiates energy generated by nuclear fusion. In a fusion reaction, two light nuclei of atoms merge to form a single heavier nucleus. The leftover mass becomes energy in accordance with the Einstein's equation E is equal to mc squared. This energy output is known as the nuclear energy. In fact, the reverse of this is true as well, such that a massive nuclei can split into smaller entities and release the remaining energy which bound them together. Let's do a quick recap of what we have learnt about nuclear energy in high school. We know that nuclear processes change one type of nucleus to another. Energy involved in nuclear processes is of the order of mega electron volts. Nucleus of an element is identified by the number of protons it has, which is represented by the capital Z. An isotope of an element is defined by the number of neutrons in its nucleus. All isotopes of a given element will have the same number of protons but different number of neutrons. Together, the protons and neutrons are called as nucleons and their sum is represented by A. Since protons and neutrons have similar masses much larger than the mass of an electron, A is a good indicator of the mass of an isotope and is therefore called its mass number. Mass of nuclei are often expressed in terms of atomic mass units, which is exactly 1/12 the mass of the isotope carbon-12. 1 U is approximately 1.66 into 10 to the power minus 24 grams. The simplest isotope of hydrogen is composed of 1 proton and 1 electron. The mass of the atom is very slightly less than the sum of the mass of the proton and electron. So if the atom is in the ground state, the exact mass difference in case of a hydrogen atom is 13.6 electron volts. This is its ionization potential. Since the total mass energy of the system must be conserved, the loss of energy during the combination of proton and electron to form the atom must come at the expense of loss of mass. Similarly, when nucleons combine to form atomic nuclei, the accompanying mass loss is released as energy. When lighter nuclei fuse to form heavier ones, the series of reactions are called nuclear fusion. But when a massive nucleus fragments into lighter components, the reactions are termed as nuclear fission. Note that both of these are forms of nuclear energy. The nuclear energy is different for different elements. We know that through this graph. This graph, called the binding energy curve, is considered to be one of the most important graphs in physics. Notice two things here. First, the typical binding energy per nucleon value ranges from 6 to 10 MeV with an average value of around 8 MeV. In other words, it takes several million electron volts to remove a nucleon from a typical nucleus as compared to just 13.6 electron volts required to remove an electron from a hydrogen atom in its ground state. This is why nuclear force is referred to as the strong force. Secondly, the graph rises at low values of A, peaks very close to an A equal to 56, which is for iron, and then tapers off at higher values of A. The peak value suggests that the iron nucleus is the most stable nucleus in nature. It is also why nuclear fusion in the core of stars ends with the production of iron. We'll get to that later. The reason the graph rises and then tapers off has to do with competing forces inside the nucleus. At lower values of A, attractive nuclear forces between nucleons dominate over the repulsive electrostatic force between individual protons. But at higher values of A, the repulsive electrostatic force becomes much stronger and dominates over the nuclear force. And these forces then tend to break apart the nucleus rather than hold it together. Let's understand this using our Sun as an example. One helium nucleus contains 2 protons and 2 neutrons. A series of nuclear reactions that we'll discuss later in this video involving 4 hydrogen nuclei are involved in creating one helium atom from hydrogen. Mass of 4 hydrogen atoms is around 4.03 atomic mass units, while the mass of one helium atom is 4 atomic mass units. Taking the difference, one can find that there is a mass difference of around 0.0287 atomic mass units, or about 0.7%. This mass goes into binding the helium atom and hence is called the binding energy of the helium nucleus. Now, we can calculate that the total energy released in the formation of one helium atom in accordance with the Einstein's equation can be given as 4.3 into 10 to the power minus 12 joules. We also know that the solar luminosity is around 4 into 10 to the power 26 joules per second. So the number of helium atoms produced per second can be obtained by dividing these two quantities and comes out to be 9 into 10 to the power 37 atoms. This means that around 600 million tons of hydrogen fuses into 596 million tons of helium every second in the Sun. But fusion reactions are not possible in the entire Sun because the temperature changes as a function of radius. Models in agreement with data suggest that in Sun, only about 10% of the mass in the core is hot enough to sustain nuclear reactions. So the total energy available in the core in the form of this mass comes out to be 1.26 into 10 to the power 44 joules. So once again, if we assume that the Sun's energy output remains constant over its lifetime, the main sequence lifetime of the Sun, which means the time for which Sun can sustain its power output by converting hydrogen to helium, can be given by the ratio of the total energy that is available in the Sun's core divided by the luminosity that we obtain from the Sun per unit time. We find that this quantity comes out to be about 10 billion years. And currently, the Sun is around 5 billion years old, which means it has exhausted only half of its fuel. But we know that the nucleus is positively charged. So does physics even allow nuclear reactions to occur in stars? Note that there are two different forces acting in an atom. The electromagnetic force, which is a long-range force, and the short-range nuclear force between the nucleons, which binds the nucleus together. All elements have a positively charged nucleus. So when two nuclei approach each other, the particles involved must first overcome the electric repulsion and collide with each other, forming new nuclei in the process in order to accomplish nuclear fusion. In other words, the Coulomb potential energy barrier must be overcome. The region inside this potential energy curve is the potential well governed by the strong nuclear force which binds the nucleons together and dominates the Coulomb repulsion between protons. If raising the temperature of the system can overcome this Coulomb barrier, then, in accordance with classical physics, a temperature of around 10 billion Kelvin will be required for the two protons to collide. But the temperature in the core of the Sun is only of the order of about 10 million Kelvin. Then how is the nuclear reaction possible? The answer to this question lies beyond classical physics. Recall that in accordance with the Heisenberg's uncertainty principle, it is not possible to determine a particle's momentum and position to unlimited accuracy simultaneously, which implies that the uncertainty in the position of one nucleus colliding with another may be so large that even though the kinetic energy of the collision is insufficient to overcome the classical Coulomb barrier, the nucleus may find itself in the central potential defined by the strong force of the other nuclei. This phenomena, known as quantum tunneling, has no classical counterpart. Quantum tunneling can take place when the two particles are within 1 de Broglie wavelength of each other. In case of hydrogen, it turns out that quantum tunneling is possible at a temperature of around 1,000,000 Kelvin, which is consistent with the temperature and pressure conditions found in the core of the Sun. As discussed in a previous video on stellar spectra, the Maxwell-Boltzmann distribution describes the distribution of velocities of particles in a gas. But this also implies that only a small fraction of very high energy particles are able to overcome the Coulomb barrier and can trigger nuclear reactions in the core of stars like the Sun. But as shown here, this small number of particles is insufficient to account for the solar luminosity. So, in order to determine the rate of reaction in a given energy interval, one must describe the number density of particles having energies in a specific range together with the probability that they can actually tunnel through the Coulomb barrier. The total nuclear rate can then be calculated by integrating over all possible energies of the nuclei. This is shown graphically in this plot. The energy corresponding to the point where the gravitational potential energy overlaps with the Maxwell-Boltzmann distribution is called the gamma peak. The likelihood that a nuclear reaction will occur is a function of the kinetic energy of the collision of the particles involved as well. The gamma peak arises from the contribution of the high energy tail of the Maxwell-Boltzmann distribution and the Coulomb barrier penetration term. The curve peaks at energy E0. As a consequence of the gamma peak, the greatest contribution to the reaction rate integral comes in a very narrow energy band which is highly dependent on the temperature of the gas and the charge and mass of the constituents of the reaction. This implies that particles with 3 to 10 keV of energy can overcome the Coulomb barrier, and given its temperature, we know that there are plenty of such particles in the core of the Sun. Now that we have established that nuclear reactions can occur in the core of stars, let's take a quick look at some of the reactions themselves. Note that each reaction in the series of reactions that we are going to discuss here will take place with a different reaction rate because the Coulomb barriers and cross sections involved for each particle are different from others. In stars like our Sun, the density and pressure in the central core is large enough that hydrogen can fuse into helium through the proton-proton chain reaction, also known as the pp chain. The slowest step in this series is the first step, which requires a proton to decay into a neutron. This kind of decay involves the weak force, one of the 4 fundamental forces in nature. The rate of energy production in the pp chain reaction depends on the 4th power of the temperature. The pp chain reaction is responsible for converting hydrogen to helium and production of energy in stars like our Sun and some stars which are even less massive than our Sun. Two-thirds of the times, the pp chain proceeds by combination of two hydrogen atoms which result in a deuterium. This deuterium, when it reacts with a hydrogen atom, produces helium-3, and most of the time, two helium-3 atoms can combine to form the stable helium-4. This reaction is called the pp1 chain reaction. On the other hand, about one-third of the time, the helium-3 will combine with an existing helium-4 to create beryllium-7. This beryllium-7, most of the time, will capture an electron to form lithium, which will again combine with a hydrogen atom to produce two helium-4 atoms. This is called the pp2 chain reaction. On the other hand, occasionally the beryllium-7 will combine with a hydrogen atom to form a boron-8, which can spontaneously decay into a beryllium-4, a positron, and an electron neutrino. The beryllium-4 will then disintegrate spontaneously into two helium-4 atoms. This is called the pp3 chain reaction. There's another way to make helium out of hydrogen, using carbon, nitrogen, and oxygen as catalysts, as shown here. This set of reactions converts 4 hydrogen atoms into a helium atom, while all the other nuclei remain conserved in the complete set of reactions. But every once in a while, the CNO cycle branches off, as shown in the bottom set of reactions. The energy production rate in the CNO cycle has a much stronger dependence on temperature, which goes as temperature to the power 20 compared to the pp chain reaction, where the rate of energy production is only temperature to the power 4. The CNO cycle is the prime source of production of energy in stars more massive than the Sun. Notice that when hydrogen is converted into helium by the pp chain reaction or the CNO cycle, the mean molecular weight of the gas will increase. If the temperature and density of the gas remains constant, the ideal gas law predicts that the central pressure will decrease. As a consequence, the star will no longer be in a state of hydrostatic equilibrium and will start collapsing under its own gravity. This collapse will further increase the temperature and density in the core to compensate for the increase in the mean molecular weight of the gas. At sufficiently high temperatures, the helium atoms inside the core will begin to burn, with a shell of hydrogen burning around it. This process of converting one element into another through nuclear fusion is called nucleosynthesis. The main sequence is only populated by stars which fuse hydrogen into helium. At even higher core temperatures of around 100 million Kelvin, a three-body reaction called the triple alpha process or TAP can convert helium to carbon. The name of the series has an interesting story behind it. Historically, the particles of unknown origin were discovered in radioactive decay process and were termed as alpha particles. Much later on, Rutherford discovered that the alpha particles were nothing but helium-4 nuclei. Since 3 helium-4 nuclei are involved in this series, it is called the triple alpha process. The rate of energy production in the triple alpha process is even more strongly dependent on temperature, which goes as temperature to the power 41, implying that an increase in temperature by 10% will lead to 50 times more energy output. Moreover, at such high temperatures, elements such as carbon and oxygen can also interact with helium-4 nuclei and produce oxygen-16 and neon. At even higher temperatures of around 600 million Kelvin or so, carbon and oxygen will start burning to produce other higher order elements and more energy. Some examples of such reactions are shown here. Remember that more massive is a star, more is the likelihood that it will continue to attain higher and higher temperatures to facilitate ignition of higher order elements in its core. But this process can continue only until it forms iron. But what happens then? Well, we'll learn about that in the upcoming videos in this series of videos on stars. In the meantime, do let me know what fascinated you most about the energy production in stars. Let's chat in the comments section. And don't forget to like, share and subscribe to this channel. I'll see you next week. Until then, take care.